Hello, everyone. This is session in which we'll talk about design guidelines for OCP NIC 3.0 secure firmware based on what got specified in OCP NIC 3.0 spec. I'm Hamel, and I'll be presenting this with my colleague Eric. I'll cover the first part, and then Eric will cover the second part of this talk. And our agenda is, I'll start with motivation for the secure firmware, talk about security features that went into OCP NIC 3.0 spec, and then Eric will go over design and implementation guideline for secure firmware, and then we'll conclude the talk. So first, why secure firmware? So as we know, NIC or network interface controller, they're becoming critical component in your server or data center infrastructure. They're part of your hardware, and in today's distributed world, cloud computing type of infrastructure, NIC is essential for server communication. And with the modern NICs, there are a number of features that are supported by NIC. They are either running data plane or control plane firmware, and that firmware piece is running embedded inside the NIC on embedded cores. So this firmware handles a lot of complex tasks of managing NIC to doing the data path functions, and it depends on the NIC implementation. But as we have seen with data center on the host OS, which is using this NIC for communication, there has been a lot of attacks that people have done in the past. Now NIC firmware is becoming a new attacks surface within the data center servers and the infrastructure that you have put together. So it's very important to have this firmware really being protected from this kind of attack. And that's why in today's data center and cloud infrastructure, secure and authenticated NIC firmware is a must. And that's the motivation that went into with OCP NIC 3.0 specification. As a part of specification, the community agreed that we need to have a set of security features being specified for NIC implementations. So next, I'm gonna talk about what are those security features that are currently in this specification, and how secure that makes the NIC implementation. So the spec, as it's specified, it recommends secure firmware to be running on the NIC. And specifically, the called out features are, first one to begin with is digitally signed firmware. What this means is the firmware that is running on the device is an authenticate firmware, which has been signed by the device vendor or whoever is providing this product and was involved in signing the firmware. So the digitally signed firmware is your first secure feature in the NIC. Now, once you have that digitally signed firmware, you also want to make sure that that firmware, when it's been updated, is that update part is always valid and authenticated. And this is where the signed firmware comes into picture. Before you update the firmware, you can verify the signature of that firmware that's being updated to prevent any unauthenticated type of firmware updates. And this all we'll get into more details, but implementation wise, this builds the root of trust for that firmware. And you want to make sure the way OCP NIC 3.0 recommends, once you have this secure features, secure firmware, authenticated update, there should not be any backdoors or any mechanisms which allows an implementation to have bypassing of firmware authentication, because that kind of defeats the purpose of having digitally signed firmware, which is being securely loaded and securely updated. So those are some of the critical piece for the firmware in terms of security. And then when this firmware starts running and when you're booting the device, the secure boot, what this means is when the firmware is first loaded, before it runs or executes any of the functions, it is validated, and that's how it is securely being booted. And then you can have a chain of trust where you can build from your bootloader to your runtime firmware, and through each stage you are validating the firmware before it runs. So that's one of the important aspect during the runtime. And also built into that secure boot, you also want to have recovery from boot failure. So what I mean by that is if you have two images and then one you're maintaining for redundancy, and during boot one of them fails, you should be able to fall back to a second image. That's one example. Other one could be you always keep a recovery image. So if for some reason your secure boot fail, you can use this recovery image to boot from that, and then update your firmware to a well-known or good state. So these are all specified in OCP NIC 3.0 spec as recommended features. We believe that modern NIC implementation should support all these security features. And next, what we'll do is I'll hand it to Eric, who will go over the design consideration as well as Broadcom secure firmware implementation. Eric?
Thanks, Emil. So what I'd like to do is just discuss a little bit about what the security design goals are for secure firmware. So if you look at typical servers, there's a host, and then there's some number of typically PCIe or other devices in the system. In this example, we'll use an OCP 3.0 NIC. And big picture, the first thing you want to be able to do is be able to, for the host to identify what devices are present in the system. And this is essentially called device identification. So you ask the question, you answer a challenge. The challenge comes back with particularly a defined certificate, and that certificate cryptographically defines whether the devices that are in the system. The next step that typically you want to do is to understand what is the security state of devices that are inside of your NIC or inside of your server. So the typical way of doing this is what they call an attestation flow. Now, the attestation flow has been a well-defined set of primitives that were started with the Tarsa Computer Group and expanded by USB 3.0. And essentially what it is, it comes down to a platform measurement register. Now, platform measurement register is a cryptographic hash you can look at it as a path of the signed path of components that generate the signature for your system. So one way of looking at this is that you have a set of secure firmware that generates one message. You then extend that message with your secure NV parameters, and other components in the system are chained together to create this platform measurement register, or what at the end of the day ends up as an attestation quote. This is then signed with that device identity and given back to the host as proof that I have a defined set of software and security state of the device. The host will typically use an attestation service to understand whether that attested to set of parameters is valid in the system. And this goes through all the devices that are in the system, and you build up what they call platform manifest of all the devices in the system. The second and the last thing is that there may be devices that need to essentially identify that the host that they're talking to. In this case, essentially, if you look at a TPM module or other types of pieces that will have cryptographic keys, typically what you would like is not only for the host to authenticate the device, but once the device has been enrolled, you want to make sure that the device essentially authenticates the host. And this is what they call host identification. So when we go through these when you go through this flow, essentially what customers typically want to look at is some big picture questions. So what devices are in the system? We've talked about this cryptographic identity. Is the firmware genuine? Typically, you want to be able to boot only authenticated firmware that's in a root of trust. Therefore, you know that if you have containment of the keys, you know that the firmware that's running here is only rooted in this root of trust. The approved firmware is done through the attestation flow that we discussed. How do I prevent older firmware or firmware that may have vulnerabilities in it from running? Typically, anti-rollback counters are used so that essentially you roll those forward and then older firmware cannot run. And then finally, what is secure? And one of the ways is to make sure you're secure or secure to within some set of parameters is you define a threat model, which the OCP incubator security group has done, and you define a very specific security boundary, and then you analyze the system in that realm. And when you go through that model, you understand what threats are in scope and what threats are out of scope, and you can really understand and have a good understanding of how secure your device is. So now that we've kind of set the stage for the design goals, what we'd like to do then is kind of talk about how Broadcom has designed in their OCP 3.0 NICs their secure firmware. Okay, so if you take a look at our implementation of this in our latest NICs, we have, if you start at the bottom, or we start at the one, our cryptographic identity is based upon DICE. Trusted Computer Group has a group called DICE that generates a set of identity based upon a device configured secret. And then we also embrace the Riot infrastructure, and the Riot infrastructure takes that device secret and generates a set of device identity keys and a set of attestation keys. From a ROM-based perspective, we have a ROM-based bootloader that basically only allows signed firmware to be run on the device. We integrate with both Cerberus and DMTF. Cerberus is an OCP contribution that basically standardizes the attestation protocol between what they call a primary root of trust and an alternate root of trust, which is in the device. We also work with DMTF with their secure protocol data model, and that's to be able to run a similar type of protocols to the BMC around authentication and essentially attestation. Finally, one of the key things we also have on a device is we have secure storage that we can essentially store our root of trust, this device secret that I talked about, and any anti-replay counters that we have. So this is the basis of Broadcom's OCP 3.0 secure firmware. Okay, so call of action. So, as Hemel and I have talked about, OCP 3.0 secure firmware is essential going forward. Every customer we've spoken to said you need to be able to secure the firmware in your server. So going forward, there's going to be no real, there's going to be no choice but to do this. We've talked about secure boot, identity, and attestation. These are real, these are the key aspects of being able to deploy security for NICs. Finally, what I'd like to talk about is that there is an OCP security incubator that has that's in the process of publishing four specification. One is on attestation, one is on secure boot. There's a threat model spec, and there's a couple others. So if you're interested in this, please join that group. And the other piece is that security is only really secure if you have open standards. So really embrace the OCP Cerberus, DMTF, NIST, and other security groups in the that do these things. At this point, I think we will open up to questions and answers.